So we have been discussing about matrices. So now what we'll do is today we'll start our discussion with what's called as linear transformations. So now first of all we'll see what a transformation means. So what do we mean by this transformation? So if you have read about functions, and we had detailed discussion on functions. So if you give some number, suppose x, and then you have a function f of x, this takes this number as an input and it gives some output from this function. So it transforms somehow. So this input got transformed into some output by using this function. So similarly in our matrix and in our linear algebra, you will have a vector. Suppose you have vector 2, 3. Now you know that what a vector is. So what you can do is you can apply a transformation on this vector v. Suppose this vector v is there, and now this vector will be transformed somehow. So let's suppose it will be transformed for 4 and 5, something of this sort, roughly. So you had a vector, you did some operation on it. That operation is basically transformation. If you see the whole that 2D space in which we had, suppose coordinates, we had an origin, and this vector 2, 3, suppose it's like this, and you did something to this vector, and what happened? This vector was, suppose this is the vector that we finally got. So somehow we transformed this vector. So why is it called linear transformation? Because we need some properties out of it. That's why we call it linear transformation. So now if you see this, so simply what you should remember about linear transformation is if you have a vector and you apply something onto it. Okay, generally you do it what's called as matrix transformation. You will apply a matrix onto that. So the concept of matrices comes from transformation. It comes from this transformation. So we'll have a vector in some space, and after that what we'll do is we'll do something onto that vector space, and you will see that whole of the vectors get transformed. Okay, but the properties that it should hold is that, suppose the first property that you have, suppose you have two vectors, you have this vector u and you have this vector v. So now what you can do is if you add these two vectors together, you know that you will get a resultant vector, because we have read about the addition of two vectors, and then you apply some transformation onto this. Okay, so what you do is you have a vector u and you have vector, suppose this is u and this is v vector, and now you added these two vectors and you know how to add the vectors together. So what you do is after that you applied some transformation. Now you know what transformation means. It will take these vectors somewhere else. Now if you apply the transformation separately, you will apply t of u and you will apply t of v separately, and then you add these vectors together. So initially what were you doing? You were adding the vectors first and then applying the transformation. So in the second go, what you are doing, you are applying the transformation separately, then these transform vectors, you are then adding these two things together. So if these two things are equal, so this is the first property that linear transformation should have. Okay, this is the first property. And second property, if I tell you, the second property is that suppose if you have a vector and you scale it up, you have a vector scalar c, you are scaling this vector, and then you are applying some transformation onto this. And then if you have a vector and you first apply transformation and then you scale, and this also should be equal. So if these two properties are holding for a transformation, that transformation is called a linear transformation mathematically. So now you saw that a transformation means you have a vector and you do something to that vector, and you take this vector and you change its coordinates. Suppose if you talk about, let's say, 2D coordinates, if you have a vector which is in 2D 2, 3, so you applied some transformation and you landed that vector to 2, 5. So now what you have is linear transformation should have these two properties, that if you have two vectors, if you add them up together and then you apply the transformation, it should be equivalent to as if you apply the transformation of the first vector, then the second vector, and then you add these two transformed vectors. And the second property that it should have is if you have a vector and you scale it up by c, then you apply the transformation. This should be equivalent to if you apply the transformation first, then apply the scaling. And these two things can be visualized. So by in visualization, I'll show you that the transformation, if you see this, suppose if you see 2D coordinate plane, so that will look something of this sort. Suppose you have some x-axis and y-axis. This is your y-axis and this is your x-axis, and this is your origin. So these two properties ensure two things. The first thing that it ensures is these lines, the lines I am drawing, they should remain parallel. They should remain rather evenly spaced and parallel. Okay, and first, because the space right now that you see is what, if you see any type of suppose vector space, if you see R2, R3, you can make up these boxes. Now after applying transformation, because each of this vector can be represented like this, suppose this is a point, this is a point, this is a point, and correspondingly each of the vector can be shown as a point. So what I'm saying is if I draw these grid lines, so now what will happen is if I apply some transformation on this, whole space will be transformed. So what I want from that transformation is that these lines should be equally spaced and origin should be fixed. So this origin should not move. So if these two properties visually, if these two properties are there, so it will ensure that these two things are there. Okay, it will ensure that if you apply any transformation, so if that is linear transformation, it will sort of abide these two rules. Okay, we'll go to the visualization to see this. So first I'll show you that if I want to transform a vector, how will a vector look like, because every time I'm talking about a vector, as a computer science person, the thing that should pop into your head is two numbers. Suppose couple of numbers, you have an array of numbers, 2, 3 or 4, 5, all of these are vectors. So now if I take an example of R2 means that I have x-axis and a y-axis. I'll have two-dimensional coordinate system. So in that I have a vector. So if I do something onto that, so whole of the vector space will be transformed, and all the vectors that are in there will be transformed somehow. So we will see it visually. After that we will have further discussion. So what I'll do is I'll copy paste some code, and then you will have to pause the video over here to read the code, but it is not that difficult to read the code. So what I'll do is, so these are just matplotlib. So I'm initially having some, suppose if I have a vector over here, if you see, I will directly run it and I'll show you the visualizations. So if you see this code, this is the code that is written over here. So what this code does is, you will have two basis vectors initially. So you have this vector, you have a basis vector, suppose I0, you have this 1, 0 and 0, 1. These are the two basis vectors, that are original basis vectors. So what I do is, if I want to transform this somehow, what I am doing is I am applying some operation onto it, I am applying some transformation onto it. So what I am doing is I am applying the transformation this. If you see, there is a matrix defined over here somewhere. So this matrix that you can see over here, so this is the matrix. So I am applying this matrix, that matrix is defined somewhere, this matrix which I have defined over here. So once I am calling this, so I am defining this matrix over here. So if you see this matrix, so this is np cos theta, np sin theta, np sin theta. So there are 4 values. So the first column is sin, cos and sin, and the second is minus sin and cos. So this is the matrix that I am applying. So if you know that, what I am doing is I am multiplying this with these basis vectors. So if you see this, so this is rotation 90. So if you see the whole space at the background is this light blue one. If you see, these are the ones that were originally there. So if you see this, so these grid lines, the grid lines that I am pointing towards, so this grid line, this over here, so this was the original space we had. So after we multiplied this with the matrix, so this matrix is called rotation matrix. If you see, this is rotation 90 degree. So this matrix that I showed you over here, the matrix, this one. So if I write it over here, so this is cos theta, so this is minus sin theta, and this is sin theta and cos theta. So this matrix over here, when it is multiplied with this 1, 0, 0, 1, so these are my basis vectors. So it somehow transformed these basis vectors. So how does it transform? It rotates the whole space. So if you see these grid lines initially, so grid lines were like this. So you know how standard space looks like. Afterwards, if you see these points, so if I now join these points and draw the grid lines, so what will happen is, this is rotating the whole space by 45 degree. So if you see this, so this is one line, say this line is there, and this is the other line. Okay, sorry for the bad drawing, but if you see this, so this grid lines, if you see clearly, they somehow got transformed by 45 degrees. So how can you see this? So these were the original vectors. So you have ordinal vectors, this red I cap, and this was your j cap. So this was your I hat and this was your j hat. These were the standard basis vector in R2. But after applying this transformation, rotation 45 degree, the matrix that I showed you, so what happened? So this is the vector and this is the other vector. So this is my transformed I cap and this is my transformed j cap. So whole of the thing got shifted by 45 degree. So this is what I mean by linear transformation, because if you take any vector in this, so you will see the two properties that I spoke about are there. And if you see visually as well, so still you will see that the origin remained fixed. So you saw this, the origin was there initially, the same origin is there. Now once I rotated the whole vector space, you will see that these lines were still evenly spaced and parallel. So is it clear? Any questions so far? So this is the first transformation that I showed you. This transformation is called rotation. So if you have any questions, I can take them. So these are the two questions received. The first question was, do we apply this transformation on a single vector? So when I speak about this transformation, t of suppose v, and it will be transformed somehow. So do we apply this only on a vector? So the question is similar to, suppose if I am defining a operation that is multiplication. If I say multiplication by 2, because multiplication is a transformation. If I multiply 4 multiplied by 2, this is 8. If I multiply 9 multiplied by 2, this is suppose 18. So now you see this multiplication by 2 is a transformation. But when I am defining this multiplication by 2, so it is actually at an instance, it is applied to only a single number. But it should be applied on all the numbers, because multiplication by 2 is valid on all the real numbers. Similarly, when I'm talking about these transformations, so these transformations at a point of time can be just applied onto one vector or bunch of vectors. But whatever vectors are in the vector space. So this transformation should be defined that way. So that's why whenever we showed the visualization, you saw that I was showing the whole space there, because whole space contains all the vectors that are in that vector space. When I'm defining a transformation, I must show that what is happening to all the vectors at once. If I have to define a transformation, it should be applicable to all the vectors. That's the first question. The second question is, how do we determine what is the transformation that we have to do? So as I say that these matrices, they find application in machine learning, they find application in graphics visualization, they find applications in simulations and all the time. So I'll just give one example. So in graphics and visualizations, in graphics, so generally you have, if you have suppose some 3D object, so you have different types of representations. So one of the representations is called as 3D point cloud representation. So in this representation, you have a file in which you are given points, and each of the point is given 3D coordinates. Suppose you are given some body, say, and 3D object is given, that is a man, and you have to perform something with the man. You have to maybe rotate it with 45 degrees. You have to make this picture move. So what you do is, because this is a point cloud representation, so in this, each point should be transformed somehow. So if you want to make this person walk, so now you know that each point should somehow move the space. Initially it was on the screen at this instance, at suppose t is equal to 0, it was at this point. Now at t is equal to 1, it should be here. Okay, and I should see the transformation happening in real time. So this is how we determine the transformations, and then accordingly we have to transform the whole space. Consider this, that man is living in a 2D coordinate system, and now you have this representation. So once you apply these transformation onto each of the point that is given in this 3D point cloud, so you will see this person is transforming. So actually that's an illusion that is created by these machines, because it performs what's called as each time, because a point is a vector. In computer science, a point can be treated as a vector. So initially this point was like this. Suppose if the person is dancing at time, suppose t is equal to 1, his hands will be up. So now how can you move, how can you suppose his hands are right now up and it can be like down like this. So you're moving this and this position to this position. Now you have to transform all the points which in all these arms. So I hope that you got the answer to the second question. Coming back to what we're doing in the linear transformation. Now if you see this, so if a vector is transformed, so the point is, suppose I will just make a simple vector. Suppose you have this vector which is 2, 3. This is a vector. Suppose this is.
Yeah.
So now if you see, this is my vector. Suppose this is my vector, and this vector say is of, suppose यहाँ पे अगर मैं एक vector बनाता हूँ. So if you see this vector, so let's make it like this. So say this is of say some 2 units, and say this is of 3 units. So this vector will be represented by 2, 3. So if you see this, so now what you have is, you have to go 2 units right side, you have to go 2 units on x-axis, and you have to go 3 units on y-axis, suppose. So you will reach at this vector. So what I do is, if I apply some transformation onto this, say suppose you have this vector 2, 3. So what I do is, I take some matrix. Suppose what I do is, I'll take a matrix. If I take 1, 0, 0, 1, so this is the identity matrix. You have heard that it does nothing to a vector. So why do we call this? So now you know that these two vectors are basis vectors. So these are my basis vectors. So they are my basis. So this is my, suppose, I cap, and this is my j cap. So if I take this, so you know that these are my unit vectors. So how can we represent a vector? You can represent it in basis vectors. That is what we have discussed in the previous lectures. So you can say that this is actually 2i cap plus 3j cap. This is how we can write this vector, because you know that you have this, any vector is a linear combination of their bases. Now the basis vectors are I cap is 1, 0, and j cap is 0, 1. So this is my I cap and this is my j cap. So any vector that is in the R2 space, or for the sake of matter, if we have a vector from any vector space, so you can represent that in the basis, in the linear combination of bases. So right now we have this 2, 3, we are showing it as linear combination of basis vectors. So now you have this. So if you suppose take this vector, now you know that this transformation should do nothing, because it is not changing the basis. So you see 1, 0 and 0, 1. So what you can do is, you can see, okay, take 2 of this. So we will see how this want to transfer. So what we want to do is, so in this transformation, you will just keep the thing that how our bases transform. So now you know that this is not transformed. So this is my I cap and this is my j cap still. These are not transformed. So by default, what will happen is, it will still be 2, 3. That is, we will get the vector back, because we are not doing any transformation to I cap, j cap. But what will happen is, if we are performing a transformation, we have to keep in the view that where are these vectors landing. Suppose I am doing this. So I am having a vector which is 1, 2, and I am having other vector. This I cap is landing at 1, 2, and j cap is landing at suppose 3, 2. Now what I am doing, so this is the transformation now. So 1, 0 and 0, 1 is no transformation. It is not doing any transformation. Howsoever the space was initially, it will keep it as it is. Okay. So now what I am doing is, I am saying you have this transformation 1, 2. 1, 2 basically means if I am performing a transformation. So where will this I cap land? So in the 2D Cartesian plane, in the 2D system that we have. So this is keeping track of the first basis vector, that is I cap, and this is keeping the track of j cap. So now what I am saying is, I am saying this 1, 0 is now transformed into 1, 2. So somehow there is something happening to this. So 0 1 is now transformed to 3 2. So 1 0 goes to another vector, so this goes to 1 2, and 3 2 goes to another vector. So the beauty about transformation is that all the vectors will be transformed, but you will have to just keep the track of base vectors. If you keep track of these vectors, you are keeping the track where the basis vectors went. So from this basis vector, what you will do is you can multiply any vector with these two things, and you will get what will happen to the other transform vector. I'll show in the visualization to justify this. Okay, let me make that visualization, and then we will see what will happen. Suppose you have some vector. So let's do one thing. So I will again show you the code window, and then we will have a discussion on that. So this was my initial transformation that we did. Let's remove this. So I'm just making, this is my formatting of the cell, how my cell should look like. So what I'll do is I'll show you the linear transformation before and after. So if you see this code over here, so this code, if you see, I have some matrix. This is matrix 2 1 and 0.5 and 1.5. So what is this now? So this is my transformation matrix. So how was my I cap and j cap transformed? So if you see this 2 1 over here, that is visible on the screens. So this is telling me, suppose, yeah, this one. So if I write it, suppose like this. So if I have say this is my 2 1, so this is suppose 2 0.5 and 1 1.5, something of this sort. So you have to decode how this matrix will be done in NumPy. So let's call this is my I cap now, and this is suppose my j cap. So these are the transformed vectors. Initially I had 1 0 and 0 1. So now somehow I have transformed this. I have transformed this 2 0.5 and 1 1.5. So these are my two transform vectors. So what will they do is I just am keeping track of where the basis vectors are landing. So if I am keeping the track of that, so give me any vector, so I'll tell you where that vector is landing. Why? Because you know what will remain constant. The one thing will remain constant. Initially I was having this 2 I cap plus 3 j cap, the example that I was showing you. So once we were having this, so if you apply transformation onto this, this linear combination will remain the same, but I cap and j cap got transformed. So what I mean by that is, so suppose you had this vector, so this was your vector v, say. Okay, so what you did is you said that I'll only keep track of my I cap and j cap. So I have applied a transformation, because of which my I cap landed at t I cap. Okay, this is my transformed I cap, and my j cap landed at t j cap. Some transformation happened, something I did with this, and it landed my transformation over here. So what I'm saying is, if this is the vector v, and now you have this transform vector t of v, so this will be equal to, again, this is the linear combination will remain the same. This 2 and this 3 will remain the same. That's what I said over here. So if you see the first property that you have, this is the first property sort of. So if you add these vectors, now what I'm saying is in a modified way. So you will have to just keep track of I cap and j cap if you know where the basis vectors went. So because you know that, now linear combination will remain the same. You can get the transformation of any other vector. So now if you see this, so you have suppose a, b, c and d. So these are your two basis vectors. This is your I cap and this is your j cap. Okay, now you know that this is where my basis vectors went. Suppose in this R2 example, this is the case, and you can have a couple of different examples otherwise. So you have a vector x, y, suppose. So now you know initial what was the linear combination. Linear combination initially was you had this basis vector, okay, and its combination. So you had a vector, you had x multiplied by the basis vector, suppose I cap. So in the initially you had I cap, and now it got transformed. So a, b, and then plus, because you are writing it as like this, 2 I cap plus 3 j cap, something of this sort. So initially now this got transformed to this AB. So now this x will still remain the same. So if you have to see how this vector was transformed, this xy vector was transformed, what will you do is you will say that initially we had suppose this 2 times of I cap. Now you will have 2 times of the transform vector, plus you will have this y. Now once you have y times, because the linear combination remained the same, but the vectors that we have basis vectors got transformed. So you will write c, d. So this is the final transformation of the vector. So you have the vector xy. So it will be transformed somewhere here, but the linear combination will be remaining same. So here this is x, not 2. So this is x. So I'll show this by the image. So that is the code I was showing you people. So you have suppose a vector, you had vectors, and what I'll do is, if you see, this is my transformation. This 2 0.5 and 1.5. Now what I am doing is, if you see this, so this is my basis, initial basis. E1 and E2 are my initial basis, and then I have a vector. Suppose 1, 2 is my vector. So if this is my vector, so what will happen is, so I will transform the vector. So how I will transform the vector? Because I know that, so if you take this matrix, if you take this 2 0.5, 1 1.5, so howsoever it transform my basis, linear combinations remain the same, it will transform the v vector. So if you see this, so this is my original space. Okay, this is my original space I. Suppose here you have, this was 2i and 2i plus, I think this was I and 2j, I plus 2j. And now if you see this v, suppose this v is not, because of if you see this v, suppose this v will remain somewhere over there, suppose somewhere over here, this v will be somewhere over here. Suppose if now you see even these grid lines are transformed, but you can clearly see this, it will still be the same. It will be one I and these two j's. So now if I draw it suppose properly, so this one I and I'll take this one and I'll take it twice. So this j will be taken twice. So the vector got transformed. So what I did is I only kept the track of these two vectors, where these two vectors landed. So this I cap landed suppose at here. So this is my I cap. So it was initially 0, 1, 0. Now it landed at suppose. So if you see this 2.0, 0.5 somewhere. And now if you see this second vector j cap. So j cap landed at over here. But this v vector, it also got transformed. But you saw that the linear combination remained the same. The linear combination, whatever it was initially, it is still the same. Okay, any doubts till on this point? So if you understood the linear transformation, now you saw this origin remained fixed. The origin that we had earlier over here, the origin that you have over here. So this origin is remaining fixed. Now the fundamental thing that you should get out of this is where we got matrices. So if you are seeing this, so we got this matrices. So now we had suppose 1, 1.5, say 0.52, something of this sort, 2.0. So now this is where I cap landed and this is where j cap landed, and this matrix is my transformation matrix. So this is my transformation. So this is my linear transformation. The matrix that I have defined over here, because this is telling me where your basis vectors are landing. So I can call this as a linear transformation. Okay, and now if you had even paid a little bit heed, if you have just seen this, and now you saw this is the matrix multiplication. This is my matrix multiplication. You people have been told to mug up matrix multiplication, but if you understood linear transformations, because you are now just saying, okay, this is my basis vector, this is my basis vector, the linear combination should remain the same. So that's what I did. So in the previous lecture somewhere I told you that, so if I have this matrix C matrix, so you can see this, so this linear combination of these columns. So if you take a column in this, it is the linear combination of columns of this matrix A. Suppose this matrix is called A, and this is X, and this is C. So columns in C are the linear combination of columns in A. How? Because you are taking the linear combinations remaining the same. This is the vector, and this is what this is telling you where the basis vectors are landing. Okay, let me clarify it a bit more. So now you have suppose a vector. You have initially a vector v, which is xi cap. I'll just make it more generic, and then we have suppose yj cap. And how to write this vector if we are in 2D coordinate system? So you'll clearly write it like this. You will say x comma y. I'll write it this way. Now this is the vector representation of this, because you know that this is a standard basis. And by definition, what are basis vectors? Basis vectors are a set of minimal vectors by the help of which you can represent any vector of the vector space as a linear combination of these basis vectors. Now what you can do is, if you now see this, so if you are giving me any matrix, so you are giving me suppose this A, B, C and D, and then you are multiplying it with this x and y. So this is the transformed I cap. So this is my T I cap, and this over here is my Tj cap. Okay, initially what I had is, so this is my, so whatever I'll get over here, so that will be transformed V vector. This is what I'll get. So now I'll get this. So I'll get linear combination will remain the same. I'll get TV. So how I transform this? So this will be equal to, so x times Ti cap plus y times Tj cap. Okay, so if you expand it in the matrix notation, it looks pretty weird, but this is pretty easy to remember. So this is what it says. If I have to see the transformation, I'll keep the linear combination same, and I will keep this basis vectors as transform basis vectors. So now if you bring matrix notation, what is T of V? So transformation you know. So this was A, B, C and D, suppose something of this sort, and V you know it was x and y. Now you know what is x. So this x is as x, and this transform vector was A and B. Okay, so what was this y? So this y was y as it is, T of j is C comma D. So this is how matrix multiplication is defined. This is the definition of matrix multiplication. Because I told you in the previous class as well, I'll show you that why is the matrix multiplication done in that peculiar way we think of it. So we are thinking, usually we have been taught like this. You take this row and you multiply with this, you will get the first entry. So if you now see it, it's pretty clear. You don't have to mug up anything. You don't have to remember this. So if you see that, what's the transformation? Transformation is a matrix which tells you where your basis vectors are landing. Okay, it will tell you initially you had basis vectors 1, 0, 0, 1, it's landing at A, B, C, D, or some other vectors you had. Now initially you had a vector xy, so xy was in the standard basis or some other basis vector. So you had, say in this case you had xi cap plus vj cap. So once you perform transformation, so what you do is you are keeping the linear combination same, and you are just caring about where did these two vectors went, and then you are multiplying it. Okay, did it make sense to all of you? Now you saw that what linear transformation is. You saw that why is the matrix multiplication defined the way it is defined. Now what you can do is you can define your own matrices. Suppose you want to define a rotation 90 degree counterclockwise, 90 degree counterclockwise. This is the answer to the question which Asif asked. How do we define it? So what you have to do is, if you have to counterclockwise rotate 90 degrees, so you know what I am doing is, I have to suppose keep this 1 0 is to be made 0 1. So I have initially my I cap was like this and my j cap is like this. So this is my initial vectors. My j cap is like this is my I cap and this is my j cap. If I have to counterclockwise rotate it 90 degrees, so what is the meaning of that? That means I'll make I cap like this. So I cap should be like this and j cap automatically will be like this. This is what I have to do. Okay. So if this is the rotation that I had to perform, so you know that what I should do is, initially I had this, I had 1 0 0 1 was my matrix, because it was my, that's why it's called identity matrix. Why? Because it is by default the way that we have defined it. Now in order to transform this 90 degrees, so I told you this is what you have to do. So if you see that, how did I got changed? So transformation is, if you see this I, now I became 0 1, and now if you see this j became minus 1 0. Okay, so this over here, if you multiply any vector with this, so that vector will be shifted by 90 degrees. Okay, if you take any vector and you multiply that vector with this, on the screen what will happen is your vector will be rotated 90 degrees. So how many of you agree on this point? So if you take this example, the question which I asked Muzaffar was that if you have a vector 2 3 and 4 5, so let's call these two as bases. So this is where my basis will land, and this is after that where my basis will land. So what I'm saying is, you can have a matrix again. You can have this matrix 4 5 6 8. Now consider this is a separate vector, and you can consider this as a separate vector. If these two things are separate vectors now, so what will happen because of this is, so the linear combination will remain the same. So you'll say 4 multiplied by 2 comma 3. So this 4 multiplied by this whole vector plus 5 multiplied by this 4 5. So 5 multiplied by this 4 5. So this will be the first column of the resultant. So you'll have first column over here. So that will be this. Okay. So now you will treat the second column. So now you have the 6 8. So this 6 can be taken and it can multiply by 2 with 2 3. So this 6 multiplied with 2 3. Similarly this 8, because linear combination is remaining the similar, and we are just worrying where did the basis vector land. Now this is 8 multiplied by 4 5. Okay, and this is the second column that will be over here. So if I now expand it, so you have this whole matrix. Okay, after this whole matrix you have this 4 comma 5. So you'll take 4 of the first column and 5 of the second column. You'll get first column of a resultant matrix. So I'll write here over here, this is the resultant, and this is the second column now. So 6 8 is the second vector over here. So second vector, you will multiply this or this with 6, and you will multiply this 8 with 4 comma 5, and then you will get second column of suppose resultant. Now what I'm saying is, if you have three matrices, you have this A, you have B, you have C. Now you should know, why do we want to care about the dimensions? The number of columns over here should be equal to the number of rows. The answer comes from this. The answer is over here, because you have this 4, you have to take a linear combination. So 1 2, suppose there you should have now 2 columns. So number of columns should be equal to number of rows over here. Why? Because you know that the columns are linear combination of columns of this. So now if you have 1 and 2 numbers, you should have 2 columns over here. If you have 1 2 and 3 rows, you should have 3 rows over here, because this is how the matrix multiplication is done. And why is it done? I told you why is it done like this, because we are just caring about the basis vectors. Now if you have these matrix A, B, and resultant is C, now you have M cross N, N cross P, and now this is M cross P is the resultant vector. So now can I say this? Columns in matrix C, they are the linear combination of columns of A. So the answer explanation is over here. So you take this is my B matrix. So this is the column 1 of B and column 2 of B, and this is my matrix A. This over here is my matrix A. These are my columns of matrix B. So what I am telling you is, I'll get some result in matrix C after this. So I am saying the columns in C matrix, so if you take columns of this matrix, there will be the linear combination of columns of A matrix. How? Because the first column will be linear combination of by 4 5 linear combination of this, and then second column will again be linear combination of this. So that's why I have written this line. Columns in matrix C are linear combination of columns of C. Columns in matrix C are linear combination of columns of matrix A. That is the code that you have to remember. किसको लगा ये भी सही है? पहले हमने देखा कि ये वाला, the first statement was this: columns in matrix C are linear combination. I should write linear combination like this. These are linear combination. This is the second way of looking at matrix multiplication. So all of you agree on this? Sharik, do you agree on this? So if you see, again I am showing you this. So I have a matrix, suppose A, B, that's equal to C. So the dimensions, you will take care of this. So what I am just telling you now is, in order to see this C, how this C is found now. So I am taking the row of this matrix and keeping the linear combination similar. I am taking one of this and one of this row, 2 of the second row. So when I am taking this, so this row 1 is formed. So row 1 is formed by 1 of the first row and taking 2 of this row, and I am taking linear combination. Similarly, if I am taking second row, so how to form second row of C? So this is the second row. So I am saying second row of C is 3 times first row of B. 3 times first row of B plus 4 times the second row of B. So this is again linear combination. So if I have to take Ri in general case, so I am computing Ri of C. So this is the Ri of C. So Ri of C is take Ai. So this Ai will be from A matrix. So this will be from A, the entry in that A matrix. So Ai of A, and then row 1 of B. Again similarly Bi. This is from A matrix, but row 2 of B. Similarly, what you will get is you can again extend it accordingly. So you will get basically what I am saying is rows of matrix C. So rows of whatever matrix C rows you will get over here. So this is the matrix C and it has this rows. So rows are linear combination of rows of B. This is what I wrote. So rows of matrix C are the linear combination of rows of B. So these are the two ways to see matrix multiply. The first way was columns in matrix C. So you have columns. You have column 1, column 2, column 3. So columns in matrix C, they are the linear combination of columns of A. Okay. And the second way to look at it is rows of matrix C, because now matrix C also will have rows, row 1, row 2 and row 3. So row 1, row 2, row 3. So they are the linear combination of rows of matrix B. Now we are talking about matrix B. So these are two ways we showed for matrix multiply. We'll see more. So I'll pause over here to take any questions if you people have. Now what we'll do is we'll see the normal way of multiplication. Suppose if I am giving matrix A, I am given matrix B and this is equal to matrix C. So generally if I have to compute suppose Cij entry. So what I do is I'll take ith row and jth column. I'll take ith row of A matrix, okay, and then multiply it with jth row of this. So generally what will happen is if I am having a matrix 1, 2, 3, 4, having some matrix 0, 4, 2, 1, something of this sort. So if I have to compute the first entry, suppose this is my C11. So what I'll do is I'll take this row, okay, I'll take this row and I'll take this column and I'll multiply these two things together. So what will happen as a consequence of this, I'll get this entry over here. So how I can write this? So I'll take A, okay, I'll take A entry from here. So what will I do is I'll take each entry from here. So I'll take the first row of this and multiply it with this. So if I have to write that in suppose summation form, so suppose what I'll do is I'll take suppose from this A, I'll take A11 and multiply that with suppose over here I have this B11 plus, then I have A say 12, this is my A12, so I'll multiply plus B21, okay. So in this case it will be only this, but if you have a bigger matrix, so you can keep on extending this. So if I have to write it similar, so what I can do is, so this is my C11 entry, so this was my C11 entry. If I have to compute C11, this was my C11. So now if I have to compute Cij entry, so what will I do is I'll take ith row. So how will I take ith row? I'll say Ai, this is my ith row of A, I am taking ith row, and I am taking Bj, jth column, Bj, okay, I am taking j of that, okay. How do I ensure that column? And then I am taking each entry, I'll write k over here and k over here, I'll write summation, this goes from 1 up to the number of suppose columns in this, so you know suppose n. So this is the shorthand representation, how can you write the C entry. So if you now expand this, so C11 will be equal to A11 B11 plus A12 B21 plus A13 B31 and so on, because we are taking rows of this. This is row A11, A12, A13 is the row, and B11, B21, B31 is the column of B. So this is the expand notation, and this over here is the shorthand notation of this. So these are the three ways I spoke so far. How many of you have done it this way? I think you have done it this way from your class 9, 10th onwards. So but these ways are also the ways that to look at the matrix multiplication. The first way which I showed you over here, and the second way which I showed, now we have discussed the third way as well. Any questions so far? There are other ways to look at the matrix. We will say them now. Method 4. So we have seen so far 3 methods. We'll see 4th method of looking at the matrix multiplication. Again similarly, I'll take some examples. Suppose I am taking example, say I'll take a simple example. I'll take 1, 4 and I'll multiply it to 7, 8. I'll do this. So this is my vector and this is my suppose a row of this. So if I multiply this, you will get a full-fledged matrix over here, because this over here is 2 cross 1 and this is 1 cross 2. So you will get 2 cross 2 matrix over here. But this is a very special matrix. So this is a special matrix. Why? I'll tell you why. Now if you see this, so this 1, 4. So how can you write this? So 1, 4 you can directly multiply it and you'll get the first entry. Suppose 1 into 7 is 7, so you'll get first entry. This multiplied by this, you'll get this entry. And then 1 into 8, this is 8, 7, 4, 28, 8, 4, 32. So you'll get this, you'll get 7, 28, 8, 32. Now if you see this, this is a very special matrix. Why am I calling it a special matrix? Because if you see 1 and 4, so this over here, if you see this, if you multiply this by 7, so this is 728. And if you multiply this with 8, so you'll get 832. So now you can see these two vectors over here. So this and this vector, they are again the linear combination of this. So they are linear combination of 1 and 4. So this is 7 times this vector, and its second vector is 8 times of this vector. Again, if you see rows of this matrix, so they are linear combination of this. So because this is 7, 8, it is 1 times of this. And if you see 7, 8, and if you multiply it with 4, you will get 28, 36. That is what we have seen in the previously. Now, and if you see these two vectors, suppose this 7 and 28, this 8 and 32, somehow you can relate it to this. This 1 and 4, if you draw it, suppose 1 and 4 looks like something of this sort. Similarly, this 7 and 28 will be on the same plane. It will be all, this vector will be just scale vector of this. Again, this 8, 36, suppose if you see this vector, this 8, 32, so this will be again somehow of this vector. So it will lie on this. So this 8, 32 will also lie on this 8 times of this. So you'll just see 8 times. You will see that these 1, 2 and these 3 vectors lie in the same line. Okay, if you take that span. Now what I am telling you, this is, so after this, so if you see this and this, so now this is called as outer product. This is outer product. So initially I was taking row and column. Now I am taking column and row. So if I have a matrix A, if I have a matrix B, I am getting resultant C. Okay, so what I'll do is I'll take outer product of this. So now I'll take it like this. I'll say 1, 2, suppose 3 and 4. So here I have other matrix 3, 0, 2, 1, something of this sort. So initially I was taking row of this and then column of this. So I was getting one entry. Now what I'll get is, if I take suppose column of this and I'll take row of this, I'll get a full-fledged matrix. So if you see, I'll get full-fledged matrix like this, which will have 4 entries. Okay, again I'll take row of this and this column of this. I'll again get a full-fledged matrix. Okay, if I add these matrices together, okay, I'll get the resultant matrix C. Okay, that's what I wanted to tell you. So these matrices are called rank 1 matrices. We have not studied what rank is, but they are called as rank 1 matrices, and you can see why they are called rank 1 matrices. Okay, because if you see columns, the columns are dependent on each other over here. This 728, it can be represented with 1, 4. This 832 also dependent. So these two are not independent vectors. Similarly for rows over here, if you see rows 7, 8 and 28, 32, they lie on the same plane as 7, 8. They are dependent. That's why I said it's a spatial matrix. Why is it spatial? So it is spatial because it has rank 1. So I can take outer product. I can take column of matrix A multiply with a row of matrix A. Okay, to get what is called as a rank 1 matrix. I'll get a full-fledged matrix over here. Then if I keep on adding these matrices, because all these matrices will be of same sizes. So if I add these matrices, I will get the resultant matrix C. So how many of you understood this and agree on this point? So if you understood this now, if you understood this, that we can add these matrices together, which we got by multiplying column of A and row of B, and you get a matrix like partial matrix of C, some part of that. Okay, after that you will keep on adding this matrix, and you will, once you add all these matrices, you will get the full-fledged matrix C. Now you will see other ways. So what you can do is, the beautiful way in which you can see matrix, suppose you have this matrix A and it's a huge matrix like this. Suppose it has thousands and thousands of columns. So you can even break it like this. Okay, you can have A11 over here, A12 over here, A21 over here, A22 over here. So these are called block matrices. So you can have a huge matrix and you can cut them into blocks. Okay, and you can compute this block. So you have now this A. You can again similarly have second matrix B, in which you can cut that into blocks. If it's a huge matrix, B11, B12, suppose this is 21 and this is B22. Now what you can do is you can compute AV. So you can compute this A11, B11 separately. These entries can be computed separately. So what you will do is, you will also get C by this. This is called as block matrix multiplication. You work in blocks. So you take this A11 and you take this B11. You can compute C11 from this block. Okay, similarly you can compute C12. You can compute C13, C14 similarly. So you can compute it in blocks. So this is called as block matrix multiplication. So matrix multiplication works in all these forms, but generally what you have seen is, you probably have seen only this method, the method that I showed you in the summation. So I think that was somewhere over like third method that we have shown. So we have shown 5 methods of matrix multiplication. These are not the methods, rather these are different ways of looking at it. Okay, if you see, so this is the method that we have spoken about, I think from here. So this is the first method. So this is method number 1. So this is method number 1. And after this is method number 2. Method 2, the different way of looking at it. And there's a 2 after this. We also showed this summation part. This is method number 3. So this is method 3, and after that this is method 4, and this block matrix representation is method number 5. So these are different ways of looking at matrix multiplication. And why is it so important? I'll tell you why is it important. Because every time we perform matrix multiplication in deep learning, that's why I want to show you all the ways in which we perform matrix multiplication. Anyway, when you look at the matrix, first thing that should pop up in the head is the visualization. Matrix is nothing but it is showing some transformation. That should somehow be ingrained into your head now. And then you should not only have a one peaked view that okay, this is the way matrix multiplication is done. So you should have these things in the view, because each time you are performing something, so each of this method will give you some different perspectives, will give you some different insights about that matrix, about that problem. So if you are solving a problem, if you know all of these perspectives to look at a matrix, okay, and then you can find some beautiful things in a matrix. Okay, this is the matrix if I look at this perspective. So if I take suppose perspective number 3 or method number 5 or method number 2 and I look at the matrix multiplier, you will see that you will derive different types of results, different kinds of results. And why is it so important? Now if you have seen GPUs are benchmarked. You have seen benchmarks in GPUs. There are a lot of benchmarks, how is it performing, like what is the FPS rate and all those things. So how you can benchmark GPUs, because GPUs generally perform matrix multiplications, okay, and they know what they can do is, because if matrix multiplication is the way that suppose we are doing it like this, so suppose we are taking it like this, so they already know. So if we have matrix suppose 1 2 3 4, so we have 6 0 8 9. This is very important for you people who want to work in systems. Suppose what you do is, if you perform matrix multiplication like this, you are taking row of this and suppose column of this. So you have heard about spatial locality, you have heard about caching. So what GPU does is, so it will do this, it will fetch 1 2. Suppose it will fetch 1 2 from the memory, okay, and it will fetch 6, and then it will directly fetch also other columns as well, because it will keep them cached, because in order to next time do the operation, because it knows I have to compute it for other rows. So whatever is used, whatever will be used next time, so it will fetch that already, it will prefetch that. Okay, if it prefetches that, then it will perform matrix multiplication way faster, because it knows suppose I am doing it like row wise, or I am doing it suppose column wise, or I am doing this row and this column, it accordingly fetches the things. Now when these benchmarks are written, you know, there are other methods to do the matrix multiplication. One matrix multiplication is called checkered matrix multiplication, checkered way of matrix multiplication, in which what you do is you take a checkered way of that. Okay, I'm just giving you the name, you can research about it. So what will happen is, you will have a matrix A, you will have a matrix B. So you will perform the matrix multiplication in a checkered way, so that you are hacking the GPU. You are not letting GPU use this spatial locality or temporal locality. Spatial locality basically means, so when the memory is being taken, when you see that if there is a miss, cache miss is there, and then it goes to the memory and fetches out the relevant data. It takes advantage of spatial locality, that is whatever is the next memory which nearest to it, because it assumes that next time probably this data will be used, so it prefetches that. So if it prefetches, its performance will be increased. Now what these benchmarks do is, they'll generally write these checkered matrix multiplication, because they know the algorithm. So what they do is, they know that this is how matrix will be prefetched. So the first row will be prefetched, and then it will prefetch first column and second column probably in the memory, because especially if you see these things lie nearly, so they are in spatial locality. If it fetches that, so it is tuned to do that. So generally GPUs are tuned to do that. Then people write these checkered ways of matrix multiplication, in which they'll multiply this and then they'll multiply some other entry, in which they'll break this spatial locality, and then they'll benchmark the GPU. So how good is GPU performing? And that's why you might have heard of concept of floating point operations. So now people are computing this floating point operations. If you see in deep learning, like if you see paper of DeepSeek, the first thing they did is they sort of quantified this. They said now afterwards, now we will quantify this. We'll say how many floating point operations are done per second. So we'll not see how fast is this matrix multiplication done. So rather than that, we will see how many floating point arithmetic operations are done per second. That's what they're called, flops, floating point operations per second. So if you can compute this, you will then say how much faster is your GPU. It's not only that it will take advantage of spatial locality or temporal locality, rather you should now compute how fast is this in terms of this. So here I'll stop the recording. I'll take any questions if you people have. So in the last lecture, we had started matrix multiplication. So in this matrix multiplication, I was telling you that we had seen a lot of different ways to look at matrix multiplication, because you know that if you multiply A and B matrices, they will give you some C result. But how to look at this result? There are different perspectives to look at it, and it will help you a lot once you are doing machine learning, because everything there is represented in a matrix. You have data, suppose X, that is represented in matrix. You have these weights that's represented in weight matrix, and you have these biases that represent as vectors. So now all of these things are represented in matrix notation. So if you know how to perceive these matrix multiplications in different ways, so it will develop your intuition once you are solving these problems. So now what we will do is, we will see that we have done this multiplication A and B. Suppose what is the geometrical notion of this? So if we take this A matrix, say A1, A2, say A3, A4, these are the 4 entries of this matrix. So we'll take 2 cross 2 matrix. Now we have this B, say this is B1, B2, b3 and b4. So how we were looking at it, the one aspect of looking at it was you will take a column of this and you will take linear combination of this. You will take whole, suppose this is your column 1 and this is your column 2, and this is your entry b1. So you will multiply this b1 with column 1 and you will multiply this b3 with this column. So you will get another column of this. So whatever column you are getting over here, c1. So c1 is linear combination of this. So now what you can think is, if you have now a vector, now let's now take three matrices A, B and C. The story will remain unchanged, but what I want you to see over here is, so this is a linear transformation. Now you know that matrix multiplication is linear transformation. So suppose you have this C matrix. Let's consider this is only a vector. Say we have this C1 and C2. This is our vector, and now you already know what this is. This is A1, A2, A3 and A4, and this is our B1, B2, B3 and B4. Okay, so the order of application matters here a lot, because I cannot do, if this is A into B and this is not equal to B into A, so the commutative property doesn't hold. That's what I want to show you. So, and this is a quite easy proof to it. You can do it even numerically. You can take all the entries and see that this is not equal, but I want you to understand the intuition behind that. Suppose you are doing this. This is my matrix A and this is my matrix B and this is some vector C which you are multiplying. So you know that matrix multiplication is nothing but a transformation of the vector. So this B will perform some transformation on C. Okay, this C1 and C2 vector will land somewhere. So once you take this B, so this B is actually a linear transformation. So what do you understand by linear transformation? That we have had a detailed discussion in the previous lecture. So you will take this and this sort of thing will apply on this, and this will take the C1 and C2 vector somewhere. Okay, and it will basically transform this. And after that you apply this A onto this. Okay, and whatever resultant vector it was, so here you will get some resultant vector out of these two things. So this is one transformation that you applied. And then what will happen is this transformation applied onto the C1 and C2, it will land this vector somewhere. Then you are applying A onto this. Okay, so once you are applying this A onto this, so now what will happen is whatever the resultant vector you had over here, so it will go somewhere else also. Okay, because this is the second transformation you are applying. Now you will see that the transformation order matters a lot. So if you even do it visually, even suppose this C1 and C2 was something of a vector like this in the vector space. So you had this 2D coordinate space. Suppose this was the vector that you had, say something of this sort. So once you perform this transformation, because you know that the whole space will be transformed. So let's say some transformation of this sort will happen. Okay, something of this sort happened to this. So this is when we applied B. B is a linear transformation. After you apply A onto this, so you know what will happen is, so this vector will be transformed. This vector, the vector that you got from the first transformation. So you'll have which I'll make with blue. Suppose you got this vector. Okay. Now what you can do is, if you apply it in the reverse order, if you apply A first and B first, then you will see that the transformations will have a different, they will have a different effect on this vector. So how do you apply transformations matter a lot. So that is, if you have a matrix A and B, that means you are applying B transformation first, then A transformation. But if you have B and A, that means you are applying A first, then B first. So what I am saying is, if you see it visually even, so you will clearly see that these two things are not equal, because one thing is transforming, then you are applying this transform on that transformation. So you are transforming a vector first, and then you are applying new transformation on the transform vector. Okay, so if you apply this transformation first, and then you are applying this B on that transformation, so these two things are quite different. That you can prove numerically also, and you also got some intuition when I was speaking to you about this. But what you can do is, you can also do the same thing by having a visual proof. So what you can do is, you can write some code easily, and in that code what you can do is, you can have a vector, say 2, 3 will be a vector, and you have a matrix, say 1, 2, 4, 5, some matrix. So you know that this is a transformation, it will do something to space. So you apply this to this vector and you will see where this vector will land, and then you will do one thing, you will have one more transformation, say 2, 4, 1, 0, something of this way, and you will apply this transformation on the resultant of this vector. So you will see that it landed somewhere. So this transformation had an impact on this vector first, and once you apply this transformation, the second transformation, it will combinedly take this vector, whatever this vector was, and it landed at a different value. But if you do the reverse order, so you will clearly see that, so if you apply this transformation first and then this transformation, you will see the results will be different. So that's why A multiplied by B is not equal to B multiplied by A. That is, it does not follow commutative property. Okay, let me also show you the visual thing. I can write some matplotlib code and I can show you that. Give me a second. So now let's take two matrices. Suppose you have two matrices, you have S and R. So S matrix is the shear matrix and R is the rotation matrix. Okay, you have seen that we can rotate matrix and you can also produce the shear. So all of these matrices have values. So if you see rotation matrix, so rotation matrix is 0, 1, minus 1, 0. It rotates counterclockwise 90 degree, that you have already seen, and this is the rotation transformation. Then you have also shear transformation. Shear basically means, so you will tilt the space and you will bend it a bit. If you have a box like this, suppose you have a box like this. This box is quite like this is a solid box, and it is at 90-degree angle. So what you can do is, if you tilt it a bit, if you sort of push it from here, so this box will become something of this deformed box. So now what you will have is, you will have a deformed box in which these things, the side walls, will get tilted like this. The problem is that I can't make it well, but I think you will get the point. So if you see, it'll get tilted a bit. So it was like this, the box was like this. When you apply shear onto this, if you apply force from here, so this will get like this. So this is called like shear force, or if you have heard about the shear stress. Okay, so the matrix for this shear is 1 1 0 1. So if you have a normal vector space of this sort, you have this vector space, say R2, we're speaking about this. So rotation, you can easily visualize it. If you apply this counterclockwise 90 rotation, so this will be rotated like this. So but if you apply shear onto this, so shear will do something of this sort. If you have a box like this, I have a box fortunately here. So if you have a box like this, say this is your box. Okay, so if you apply shear onto this, it's very hard. This box is very hard, but what will happen to this box is, so this wall will get like this, and this wall will get like this, and it will become something of this sort. Okay, it will get tilted. That's why it's called shear. So you have these two matrices now, and these transformations are represented by this matrix. So what is the meaning of this? So meaning of this is, so if you have this I cap, so I cap will land here and J cap will land here. So this is your I cap and this is your J cap after the rotation. This is your I cap, this is your J cap. That's what we have learned in the linear transformation. Now suppose if we have a vector now. So if we have vector and then we want to use this transformation. So what we can do is, we can use these things in any order. So you can apply, suppose, a rotation first and then shear first, or you can apply shear first and then followed by rotation. And you will see, once you do these things to an original vector, suppose you have original vector v1, okay, and in this case v1 will land somewhere, but in this case this v1 will land somewhere else. So this will give you, suppose, some v dash, this will give you some v double dash, and you will clearly see that v dash is not equal to v double dash. That's what you have to see. So that if you apply rotation first and then shear first, and it will transform this v1 vector somewhere, let's call that v dash. Say if you do the reverse of this now, if you apply this s first, the shear first, and then the rotation first, and this v1 will be landed at v double dash, and then you will see that this is not equal. Okay, that will establish our proof that the matrix multiplication is not commutative, that is s dot r is not equal to r dot s. Okay, I'll directly write the code and I'll show you that now, because now you understood this point. So let me bring the code screen and paste some code of the visualization. Okay, I'm just copy pasting it so that you can easily go through the code line by line. So it is the same thing that I told you. You have this matrix. So this is your counterclockwise 90 degree. If you can see over here, so this is your matrix counterclockwise 90 degree. And if you see this other matrix, so this is your horizontal shear. So this is your combined M. We call this M, shear after rotation. So you applied shear and then rotation. And then you have also seen this. This is my, suppose this is my vector 3, 2, and you want to see where will this go. Okay. You're applying, suppose, R on this, M on this, and if I run this code, this is all matplotlib code that you can easily see. If I run this, and you can clearly see over here, you can see what will happen to this. So this was your original vector. Okay, this was the rotation. Once you apply rotation and you applied shear onto this, and this is what happened. So initially your vector landed here, and after that your vector landed here. So this is the original, this is the final vector 1 3 in this case. And now if you do the reverse of this, suppose if you do reverse of this, if that is there, so what you can do here, I'm showing rather the combined transformation. What you can do is, so even if you multiply these two things together, so in this rather representation, what I'm showing is, I'm showing that I'm applying first, this is this is my original vector, this is my after rotation, and this is my shear. So what you can do is, you can even have only one matrix to show both of these two things. So you had this S and you had this R. So you know that if I multiply, this also is a transformation. Let's call that transformation T. Okay, so you can have vector v1, so you'll apply r on that and you will apply s on that, and it will be landed somewhere. And the same effect will be produced if you just multiply this, and you will have sort of combined transformation. That's what this is showing. So here if you see, original vector is this and the combined shear. So if you multiply this s and r first and then multiply it with this, so this is one and the same thing. But in this picture, if you see, so if you reverse the order over here, so if I take the original vector, this vector, and if I now apply shear first and then this, if I just change the code over here, the code that you see. Okay, so what I'm doing is, if you see these figures, so in this figure I'm applying the reverse. I can apply the reverse order. Suppose what I'll do is, so this is my r and this is my s, and I'm applying this is my multiplication, m multiplied by, this is s multiplied by r, and then I'm taking this. This is my v r rotation and this is my m rotation if I do it with final vector. So what I'm doing, I just wanted to reverse the thing. So initially if I was doing my rotation first and then shear first, I can just do the reverse of this. I can do, suppose, r of this and say s of this. Okay, you'll get the point that I was making. So if I do that, you will see that the both of these things will give you different answers. You can see that initially the vector was somewhere on the right side, and this is on somewhere on the left side. But I need to also change this code, that you can easily do that, because here I am applying shear first and then I am applying the rotation. You can clearly see that these two vectors are different. That establishes the point that if you apply rotation first, then shear first, then second time you will apply shear, it is different than applying shear first and the rotation then. So that's why this S multiplied by R is not equal to R multiplied by S. I just changed this one line. If you see, I just changed this one line. Oops, the code was somewhere here where I just did the reverse multiplication order. Okay, and this is that. Okay, initially I had S multiplied by R. You can again do it, S and R. So this is my S and R, and if you multiply this, you can see this is landing at 1,3. 1,3 is different than whatever it was landing. It was landing at some 2, something else. If you see over here, so it was landing at this quadrant, minus something, because x-axis was minus 2, something. So this vector was pretty different from that vector when you change the order of the transformation. Any questions still here? Okay, now that we have seen that there is a difference between A multiplied by B, matrix multiplication is not commutative. So what I was telling you, let's take a little bit detour over here. If you know about fine tuning in language models, so what is done in fine tuning? So there are different ways you can fine tune. So I'll tell you a couple of ways. Suppose you have a language model over here. So language model is nothing but weights and biases are there. You have these weights and biases. So once you give a token to it, it applies the weights and biases, attention, whatever it has, and it does some matrix manipulation. Suppose you give it X and it gives, say, something as an output. So if you have large language model, if you have suppose vision models or whatever you have, so you have this X, it gives some transformed X that you want. But right now what you can do in fine tuning is you generally freeze the parameters. So you'll freeze these parameters which were trained. So what you can do is you can add some couple of layers over here while you will give some more weights and some more biases. And there you're expecting, suppose this is a large language model and it was trained on generic data, generic LLM, and it was once it was given some query and it was performing very good. But what you want is you want to perform some alignment, some fine tuning on it. You are saying that I will train it on question and answers. So if I give it question, it should give me in this style, answer should be given in this style. So what has been seen that if you fine tune this, so what is happening that the capabilities that it earlier had, it is somehow losing them. Okay, so that is called as catastrophic forgetting. Catastrophic forgetting. Because whatever earlier it was doing very nicely, so it was given a query and it was answering it very nicely. But once it was fine tuned on this, most of the parameter was frozen, and then you added more weights and biases, and you thought that I'll give it more data and I'll train it with more weights and biases. Now that these things are trained differently. Now if you can see this, whole of this is a one big matrix multiplication somehow, and with the nonlinearity and etc. we can ignore that for now. And then you can also think this as another matrix, call it B. Okay, so initially what was happening is you were taking this X vector and it was going through a lot of transformations and then linearity, non-linearity. But other than that, many matrix transformations were happening, and this X was sort of projected somewhere and you were getting X dash answer. But if you now give the same X, but now the model has been changed, something, let's say, write it like this, A, this symbol B. So this symbol basically means that it was a lot of operations were performed, not just matrix multiplications, but matrix multiplication were the main operations. Now if you give this X, now this X dash is sort of, it's not very good. So this X, the X dash that now it gives, I'll have it with the star, X star. So this X star is not a very good answer. Like initially it was given X and this X dash was very good. It was in natural language, it was giving very good answers, but somehow it has forgotten some things. That's why it's called catastrophic forgetting. So one reason might be that you are doing this. So you are applying these matrices onto it and it is doing some transformation to this X vector, to this vector, to this embedding. And once you have add these more things, once you keep on adding these things, now what is it doing is it is now projecting this vector in some other dimension. It is doing some other linear transformation with this. So maybe that might be one of the reason that it is forgetting some things. And even if you suppose just within this model, if you have some suppose transform heads and you have some weights and biases that you wanted to change, still you have this issue of forgetting. You have this issue of catastrophic forgetting. One rationale might be that it is performing different matrix manipulations. And we cannot assume that if we have some model trained which is called as T, and then we want to augment the model and we'll just fine tune weights and biases, we might have to think of better techniques to do that. Okay, if you have to do what? So if you have to augment it. So what I mean by augmentation is, so if it is already good at one skill, it's not necessary that fine tuning will make it, just give it one more additional skill and it will not forget other things. So it will forget because you are anyway making some change into how computation is being done. So initially it was doing some matrix manipulations. Now after adding more weights and biases or training those more weights and biases, it is doing different computation. So it is expected that the forgetting might happen. No, it might not. It's not the case. It might happen. It is happening basically. But you should make a you should sort of find new techniques. So if you want to augment a model, if some model is very good, suppose on some task, some natural language, generic natural language, if you want to be very good at medical queries, so you need not to probably fine tune. There can be some other things as well. Fine tuning is good when you don't care about the earlier tasks. So suppose if you are caring about only medical stuff now, and you have a model which is performing very good on general natural language, so you can take that because it is better initialized. It's already knowing some stuff. Its weights and biases are already in a good range. So you can fine tune it, and it will now be very good at this medical task as well. And maybe if you don't require this, okay, if you suppose don't require the capability that it earlier had, it was very good at generic natural language, so then you can fine tune. But the main problem of fine tuning is this catastrophic forgetting, because people think that we can fine tune a model and we can augment its capabilities. So that is not going to be the case, and it is forgetting. And I have also shown you the paper where they have done some empirical studies that is left as an exercise to the people who are watching this video. Okay, now you understood this. Now there are some other properties of matrix multiplication. So one property that you saw, this A dot B is not equal to B dot A, and you saw the implications of it in depth. Suppose now what you have is you have three matrices. You have A, B and C, and you have A, B and C. So can you do it like this? So can you first perform the multiplication between A and B and then do C? Or can you do first B and C and then multiply it with A? So what do you think? So this is called a property of associativity. So this is your commutativity, okay, which we said that this is not holding over here. So associativity, actually, if you see it, if you look at it, if you have got the intuition, so you will clearly see that actually the thing is, so if you have a vector x, so if I am writing A, B, C and x, so what will happen is I'll first suppose apply B and C onto this x. So it will be transformed somewhere, and then I'll apply A onto this somewhere. Okay, so it will be, so if you do it like this, A, B and C and x. So if I apply something of this sort, I'll apply C on this first, and then I'll apply A, B on this. Okay, so I'm just playing with the brackets. So what I'm doing is initially I'm taking this B and C and applying it on the x, and then I'm applying whole of this onto x. So what I'm doing right now is I'm applying C first and then applying B and D. If you see, the order of the things was not changed at all. So initially we were anyway multiplying this C, then we're multiplying B, then this A. So in the other case also we're doing the same thing. We're applying C first, then B and then A. So if you see, order of the operations were not changed. So that means associativity will hold. Because if you see it, this bracket don't care, because if you are multiplying x with this A, B and C, you will anyway take this first, then you will take this, then you will take this. This is the way to do it. But what you can do is you can combine these two things also, because we have seen that if we have AB, suppose it performs some Z. But if you keep suppose BA, that is the difference. This is not equal. But in here, if you see, you are applying BC and you are applying C first and then B first. It is one and the same thing as if you are taking brackets over here, or if you are taking brackets like this, it's one and the same thing. So why is it one and the same thing? Because anyway you are applying in the same order. You are applying C first, then B first, then A first. So how many of you intuitively understood this, that matrix multiplication should be associative, because the ordering is not changed, because we are applying C first, then B, then A, anyway in both the cases. Any questions on this? So other properties are there. You have distributive property. Suppose you have this A multiplied by B plus C, so this gets distributed. So now this is left as an exercise to people to think intuitively. So if you are thinking matrix multiplication as transformations, how is this equal to suppose A multiplied by B and then plus A multiplied by C? So why is this equal to this? So you have to think it in terms of linear transformations, and you have to paint a picture of this, as I said in this case. Okay, so one more exercise over here is you can prove it numerically also. You take Cij from this and you take Cij from this, and you apply all the matrix manipulations, and we have seen that how to do it numerically, and you will arrive at the result. This Cij will be equal to this Cij if you compute it both ways. But the honest and good proof, if it is visual and it's not, there is no trickery happening over here, because you can directly write that because we do not change the order of multiplications, you are anyway multiplying by first C first, then B, then A. So it's a proof that it is associative. And there are other properties as well. You have an identity matrix which does nothing. So you know that you have some matrix, suppose if you have 2, 3, 4, 5, and now if I am given an identity matrix 1, 0, 0, 1. So now you know why does it should not do anything. Why should it not do anything? Because you know that the first column should remain as it is, second column should remain as it is, and you know how to keep them as it is. Take 1 of this and 0 of this. So that's what this thing is doing. So if you have to multiply this with 1, 0 and 0, 1, so how you should think about it? So you say column 1. Now I'll take 1 of the first column, that is 2, 4, and 0 of the second column. Okay, and similarly how should be the second column seen? So I'll take 0 of the first column plus 1 of this column. So 0 and 1. So this is suppose 3, 5. That's why I'm writing 1, 0 and 0, 1. That's why it's called identity. So it's doing nothing. So you should now know why is the identity called identity. Why? Because you see this, how is it plotted? Now if you see 3 cross 3 identity, if you have A, B, C, D, E, F, G, H, I. This is your matrix, and if you are asked to make an identity matrix by definition is a matrix which does nothing. So it leaves the space as it was. Okay. So you have to do nothing to it. I'll say one of this. Okay. I'm sort of saying this, one of this. Okay. Because I know that I'll take linear combination of this, linear combination of columns. So how I will take that? So 0 of this, 0 of this. So 1 of the first column, 0 of this column, and 0 of this column. The final matrix, the first column of that will be A, D, and G. Similarly, for the second column, you will take 0 of the first column. Okay. 1 of this column. Okay. And none of this column again. For the third column also, none of the first column, 1 of this column. And this is your identity. Okay. Now it is pretty easy to visualize. So if you know all these concepts, now you know that why is the way this identity is defined. Otherwise, you have been taught since childhood identity matrix is this. But if you know the perspective to look at the matrix multiply the way I am telling you, so it looks so natural now. It looks, yeah, it should be there. The identity should be defined this way as is defined, because you already know that there are different perspectives looking at it. Any questions on identity matrix?